लोकल तो जल्दी आ गया
उसमें लाइक एन के लिए ज़ूम कर लो.
हाँ एन के लिए जूम कर लिया.
मतलब बी का गलत
ठीक है.
सामने एकदम सामने जाओ, सामने वाले आप लेंगे in the front. भैया और एक कागज ले लो, बहुत सारे करेंगे। Okay, so the last class we started looking at why Laplace transform is required. इसका पार्टी लगी होगी every day I see people are keep on going backside. यहाँ पे तो भी स्क्रीन पे यहाँ पे का उधर लगा क्या चाहते हैं? So in the last class we started looking at why Laplace transform is required to be rectifying that. Okay? Just you पीछे नहीं बैठना भाई, आगे बैठो. इधर से दिखेगा भी नहीं. ये वाला कंटेंट यहाँ से तो दिखेगा. आगे आ जाओ. सब लोग बैक 2 rows please come in the front. So advantage of using Laplace transform is it enables converting coupled differential equations into coupled algebraic equations and solving algebraic equations is much more easier compared to solving coupled differential equations. So that is the reason why in this course we are using Laplace. The another advantage is the use of Laplace transform. Use of Laplace transform enables you to represent your system in a much more simpler block diagram compared to the block diagram we are supposed to get in time domain. Okay. So these are the two advantages which we have seen. Based on that, in this particular case study we have seen again repeatedly the same case study we are coming back again and again. Isn't it? So in this particular case we had only one differential equation v dt by dt is given as fi. पीछे नहीं बैठना है, सामने. Please go in the front. आप भी please go in the front. So we have only one differential equation there. v dt by dt is given as fi ti minus c plus q by rho cp. Isn't it? And if we rearrange the terms, we can represent this equation as tau p dt by dt plus t equals to kd ti plus kp fsc. We said that tau p, kd and kp these are the parameters. We are going to look at what is the physical significance of all these parameters little bit in more detail as we go ahead. Isn't it? But the reason here is we have defined the process in terms of these parameters because later on we are going to represent the process directly using the generalized form. And the generalized form makes use of these parameters tau p, kd. वो स्क्रीन नहीं चल रही ऊपर वाली. So kp, tau p and kd, these are the parameters, isn't it? In this you will see that the tau p is the time constant of the process, isn't it? We will be defining what is time constant here. Kd is the proportional gain, kp is the proportional gain, but kd and kp are associated with the disturbance variable and manipulated variable, isn't it? Okay. So with this, the process is represented like this: tau p dt dash by dt plus t dash equals to kd ti dash plus kp fst dash, and this is linear differential equation. We can obtain the solution of this linear differential equation directly as shown here, isn't it? So this equation is slightly more complex, isn't it? And if you wanted to represent this equation in a block diagram form, then the block diagram is this. And this block diagram is also slightly complicated. Then we said, can we make our life more simplified in this case? So we can instead of using the solution of this particular equation in a t domain, if we take the Laplace transform, then we can represent the process in a much more simpler block diagram compared to what we are getting in a time domain. That is what we have seen in the last. So this equation again we apply the Laplace transform. What we get is tau p st dash s plus t dash s equals to kd ti dash s plus kp fst dash s, and if we rearrange T dash s is given as kd tau I dash s divided by tau ps plus 1 plus kp divided by tau ps plus 1 into fst dash. Okay, so you can see that this kd tau, or in general 1 upon tau ps plus 1, that is the transfer function you are expected to get for a first order process. What is transfer function? That also we have defined in the last class. Okay, so in this case you can see that is kd divided by tau ps plus 1 that we have defined as gd, and kp divided by tau ps plus 1 that we have defined as gp. So here gd and gp are the transfer function of the process with respect to the disturbance variable and manipulated variable. You will see that later on whenever the first order process we will be looking at. What is first order process? First order process is the process which is defined by a first order differential equation. Okay, so you are likely to get this equation. Okay, so whenever we will have a first order process, we will be directly writing down this transfer function instead of deriving it later. Okay, so with this Laplace transform, then we can have a much simpler representation of the process. You can see that pi dash s is the input, fst dash is the input. You can multiply that to a kd divided by tau ps plus 1 and kp divided by tau ps plus 1, and both the signals if you add, that will lead to a desired signal t dash s. Okay, and this particular block diagram is much more easier compared to the block diagram which we have seen in a time domain. Okay, so up to this we have done in the last class. Towards the end, in the last class, we have also defined transfer function. And remember I said this transfer function term we are going to use regularly in this course. What is transfer function? Transfer function is nothing but the equation which relates your output to the input. The equation which relates your output to the input, that equation we call it as a transfer function. Formally it is defined as, transfer function is defined as Laplace transform of output in a deviation form divided by Laplace transform of input in a deviation form. This word deviation is very, very important. Okay, so Laplace transform of output in a deviation form divided by Laplace transform of input in a deviation form, that gives you g of s. So g of s is a transfer function of the process. So g of s will be given by what? It will be given by y dash s divided by f dash s, where y dash s is nothing but the output in a deviation form and f dash s is nothing but the input in a deviation form. Input in a deviation form. Okay, so we can find out the output. Remember, ultimately we are interested in finding out yt, how my output is varying with respect to t, isn't it? With respect to time. So how we can get that? We can get ys as g of s multiplied by f of s, isn't it? And then we can invert it into a time domain. We will get yt, how yt is varying with respect to time t. That is what we can derive. Okay. Another important thing to note down here is, very often the equations we are looking at, these equations are non-linear in nature. In such cases, the transfer function you have to find out only after linearization. Don't find out the transfer function before linearization. You linearize the process and then apply the Laplace transform, and then you find out how the output is related with the input, and that equation will be your transfer function. Is it clear to everyone? Now let's take a interesting case here. So we are having, let's assume that we are having a process in which there are two inputs are there. These two inputs are f1t and f2t. These are the two inputs to the process. And there are two outputs from the process, y1t and y2t. We are assuming that y1t and y2t, these are coupled with each other. Coupled with each other in the sense that if I write down the model equation for y1t and y2t are given here. You can see that this is the differential equation dy1t by dt, and this is dy2t by dt. In both these equations you can see that in this first equation the variable y2 is there. In the second equation there is a variable y1. So both these equations are coupled, they are not independent. They are not independent because they are dependent on y1 and y2. They are dependent on each other. They are coupled. Okay. So you can see that if you are having a coupled differential equation like this, let us assume that for a simplicity, let us assume that y1t and y2t, all these variables f1t, f2t, all these variables are actually given in a derivation. So if you assume that they are given in a derivation form, their initial condition will be what? 0. Isn't it? So y1 0 and y2 0 both will be 0 at t equals to 0. Correct? So we are assuming just for a simplicity. Now once we have this initial condition known to us, these are the two equations, what we have to do? Ultimately we wanted to find out the transfer function in this case. So what we have to do? We have to take the Laplace transform of both the equations, isn't it? We have to take the Laplace transform of both the equations. So if you apply Laplace transform of this to both these equations, what we get is this will be sy1s minus y10. y10 is already 0, so that is already taken out, and that should be equals to a11 y1s, a12 y2s, b11 f1s, and b12 f2s. Similarly, if we apply the Laplace transform of the second equation, we will get s into y2s minus y20, and that y20 is already 0, so that is taken out, and this will become a21 y1s, a22 y2s, b21 f1s, and b22 f2s. Isn't it? This is what we are going to get. Now we wanted to decouple both these equations. Correct? So you can see that this equation has y1 as well as y2. This equation also has y1 and y2, isn't it? So from equation 1, this is the equation 1, I can find out how y1 is related to y2, isn't it? How y1 is related to y2, and that I am going to put in the second equation. And similarly from second equation I can find out y2, and that I can put in the first equation. If I do that, you will find that both these equations get decoupled. So you will have only y1 term in the first equation and you will have only y2 term in the second equation. If you do that, if you decouple that, then you separate the variable, collect the variable and see what you get. Isn't it? Is it clear to everyone? ऐसे नहीं समझ में आएगा, करके देखना पड़ेगा, ठीक है? तो करो. Please do it. Please solve. Let's see what you get. Please decouple the equation 1 and 2. They are coupled now. Decouple the equation 1 and 2 and see how y1 is related with f1 and f2, and find out how y2 is related to f1 and f2. Okay, that is what you have to find. Don't sit idle. Please do something. करो वैसे क्या इमेजिनरी इसमें करो. अच्छा उसके साथ करो तो एक ही एग्जाम लेने जाएगा, दोनों के मार्क्स डिवाइड कर देंगे, आधे आधे कर देंगे. ऐसा है कुछ, ऐसा कुछ अरेंजमेंट है नहीं है तो फिर करो. 0 आ गया तो बहुत अच्छा है. अगले साल फिर मुझे देखो किस तरह. नोटबुक में आपका कुछ दिखाई नहीं है। बहुत सारी नई नई डिस्कवरीज हो रही थी। अरे वो मेरा लिखा हुआ नहीं, तुम डिराइव करो, उसमें भी गलतियां होगी एक दो। So from this equation you can find out y1s. How you can find out y1s? You can take this y1 term on the left hand side. You can take y1s common, isn't it? That you will get s minus a11, isn't it? And y1 will be obtained as whatever the remaining terms are divided by s minus a11. So that is what you are getting here. Second term, similarly to this, here also you can take this a22 y2s on the left hand side, and we can take y2s common. You will get s minus a22, and y2s will be taken out. So y2s into s minus a22 will be there. So y2s will be whatever the remaining term here divided by s minus a22. So these two equations we have obtained. Correct? After that, once we have obtained these two equations, now I can put this y1s, in this equation. If I put this y1s in this equation, this entire equation will be in terms of y2s and the input f1 and f2. So it will be decoupled, isn't it? Similarly, this y2s is there. This y2s, if I put it in this equation, this entire equation will become in terms of y1s and input f1 and f2. So you can see both these equations will get decoupled by substituting these in the original equation, isn't it? Correct? So that is what we have done. So these are the y1s and y2s we have put it in the respective equation. So you can see that we have put this y2s in the first equation. We have obtained y1s, s minus a11, a12, and this y2s is there, isn't it? This y2s is there. This y2s we have replaced by this. So we have put here. Now the entire equation, what happened? What happened? Remember, see, I ignore first time, I ignore second time, and third time the same thing is happening. Then compare it to point out. If you know more than me, please come and explain. And I will see how this smile remains throughout this course. It gets vanished very soon. I am telling you this. Let the first minor 2 over, and this smile will be gone. Isn't it? पढ़ लो यार, पढ़ने का काम करते हैं हम, पढ़ लो ना। नहीं पढ़ने का है तो बता दो यार, I mark your attendance. Why you are spoiling my mood? Isn't it? ठीक है? सही समझ में आया? ठीक है. So where we are? So this y2s we can put it here, and then this entire equation is in terms of y1s and the input f1 and f2. Okay. Again we have to collect the similar terms. Remember, here y1s is there, here also y1s is there. So we can collect the terms with respect to y1s, and whatever the remaining terms are there, those will be on the right hand side. And again, if we divide that, what we get is y1s comes out to be s minus a22 into b11 plus a12 b21, and in the denominator we will have s minus a11, s minus a22 minus a12 a21. That you can figure out directly here. You can see this s minus a22 you can multiply to both the sides. So you will get s minus a11 into s minus a22 here, isn't it? And then remember, here y1s term is also there. So you can take this a12 a21 on the left hand side and take y1s common. So what you are going to get? S minus a11 into s minus a22 minus a12 a21. And this entire term will be dividing the remaining terms. So that is what we are getting. See, this is the common term which is dividing the remaining terms. Okay. So now with that you will see that this y1s now we have represented only in terms of the inputs. only in terms of the input. In this equation, only F1s and F2s is there. There is no Y2. There is no Y2. So we have decoupled the equation. Okay. So now, similar to this, again we can represent this Y1s and put it in the second equation here and do the same analysis. We can decouple the second equation also, and after decoupling, what we are going to get is this. This is the equation we are expected to get. Okay. Once we have obtained these two equations, now all these terms which are there, we can represent these individual terms as transfer functions. Why transfer functions? Why we can represent these individual terms as transfer functions? Anyone? Yes, please. Y2s is output and so if we represent this particular term as a transfer function, remember all these F1, F2, these are given in a deviation form. Let's say the only deviation is happening in F1 and F2 is not at all valid. In that case, this term becomes 0, isn't it? And if I rearrange, what I am going to get? Y2s by F1s, which is nothing but output divided by input in a deviation form, and this remaining term here will become a transfer function. So I can represent all these terms as transfer functions as per the definition of transfer function which we have seen. Correct? So in this case, we will be having four transfer functions. This will be G11. So first subscript represents the input. Here Y1 has a subscript 1, so that will be G11. So first subscript is the output and the second subscript is the input. So G11. Here this will be G12. This will be G21 and this will be G22. Okay. So that is what we have done. G11, G12, G21, G22. With that, both the equations got simplified. So these are the final equations which we have obtained. So we started with two coupled differential equations, but now we are getting two algebraic equations. Two algebraic equations which are not coupled, isn't it? So you can see that these are the two equations we are having here. Now, if I wanted to represent these two equations in terms of a block diagram, how I can represent it in terms of a block diagram? F1s and F2s are the input, isn't it? So F1s and F2s are the input, isn't it? Now you can see that F1s is multiplied to G11. So if I have multiplied F1s to G11, and also F1s is multiplied to G21. So G21 here. Similarly, G12 is multiplied to F2s. So G12 is multiplied to F2s and both are added here, and that addition is going to give me Y1. Similarly, here G21 into F1s plus F2s into G22, that addition will give me Y2s. So you can see that this simple process which we had, two input and two output, now is represented in terms of a block diagram like this. Okay. So this particular block diagram is with respect to multiple input and multiple output, isn't it? There are two output and two input, isn't it? And there you can see that here the control action is also coupled. I am not sure whether we will be able to cover that or not. But if we get the time toward the end, we will see that these are the coupled control loops. Coupled control loops in the sense that if you try to control one variable, it is going to mess up other. It will have the interaction. Okay. I am not sure whether we will get the time to cover that toward the end. Okay. Now these two equations can be represented in a matrix equation like this. Can be represented in a vector notation like this. Then you can represent y1 and y2 as a matrix input output matrix, and that will be given as G11, G12, G21, G22. This matrix is multiplied to F1s and F2s. So in a matrix notation also we can represent the given thing. Now what is the takeaway message here? Takeaway message is, if there are n input and let's say there are m output, in that case how many transfer functions we are expected to get? N into m. N into m. Isn't it? Correct. Let's look at, this is a very generalized case study. This is a very generalized case study. Okay. Now let's look at the case study which we have studied earlier. Remember, we have studied the certain reactor system. In a certain reactor system, these are the two equations which we have obtained earlier. If I recall correctly, I can go back. The same equations we have derived earlier. These are the equations we have derived. See. Correct? These are the equations we have derived. We said that the inlet flow rate is same as the outlet flow rate. So height of the liquid is not varying, but temperature and concentration inside the reactor is going to vary. Isn't it? So for this we will have these two equations, and these two equations are, if you look at, these are the two equations, and these two equations are non-linear. They are not linear. This particular term e raised to the power minus e by RT Ca, this particular term is non-linear. So this non-linear term we have linearized by using Taylor series expansion, and after linearizing, the equations which we have obtained are these. These are the final equations which we have obtained. Isn't it? These are the equations which we have obtained. Correct? Now in these two equations, there are two outputs. P and C, these are the two outputs. And how many inputs are there? There are three inputs are there. Ti is the input, isn't it? Cai is the input and Tc is the input. These are the three inputs and there are two outputs. So how many transfer functions we are expected to get? 6 transfer functions we are expected to get. And I am asking you to derive all 6 transfer functions for this particular case study. Okay, that is the take home assignment for you guys. Okay. So you are expected to get 6 transfer functions, and these 6 transfer functions will be this G11, G12, G13, G21, G22, G23. So these 6 transfer functions I want you to derive. Okay, use the same method what we have used now. I have given a similar example way back in 2016 or 15. I am telling you, hardly 1 or 2 students were able to complete it. So please don't assume that everything you will be able to do it in the class, since the examination is open. Open book examination is actually more difficult compared to the closed book, isn't it? Open book means nothing from the book will come, nothing from the previous question papers will come, isn't it? And this course is such that even if you change one S in the equation, the entire solution changes. So there are large number of possibilities to make the questions. Don't expect that you will get the questions from the unsolved question papers which is there in the book. You might got some question papers from your senior, good. If you have got, nothing from them will come. I can tell you, starting with. So unless you practice, you will have a tough time after the first mile. Typically in my course I have seen the average is 7 out of 25. That is what I have seen typically. So please go through the material. Don't expect that the examination will be easy. It is not going to be easy. It is not going to be easy, and I am determined to make it slightly more difficult, considering your interest in the class. Isn't it? I have to play this game. Isn't it? This is a game. You are playing. Isn't it? I have also to play wisely, so that ultimately that objective of, what is the objective of this course? I have to make you understand this course somehow, and I will make sure that is what that happens towards the end. Isn't it? Correct? So if you play it smartly, I will play it even more smartly. Okay? जो पढ़ाई करेगा उसको आएगा, नहीं करेगा उसको नहीं आएगा. तो बॉटम लाइन नहीं. ठीक है? Okay. Now this is a very interesting. Okay, this is that if you understand these two slides, then most of the things you will understand in this course. Okay. So far we have started. So see how we have started in this course. We started with why process control is required. That is what the first class was all about, isn't it? Why process control is required. We said process control is required for suppressing the effect of disturbances on the system, stabilizing the inherently unstable process, and optimizing the process. These are the three main reasons for which the process control is required. Then we said, okay, we have understood that why process control is required, and we have also understood that process control is nothing but what? Adding some external intervention, isn't it? But you can add the external intervention only and only if you know your system well. Knowing the system is what? Either you know your system by doing large number of experiments, or either you know your system by representing your system in terms of equations. We said the second option is better for us, primarily because very often whenever we wanted to design a complete plant, we usually don't have the plant available with us. We have to design it a priori so that we can construct the plant after that, isn't it? So we said that okay, equations are something on which we have to rely, isn't it? So there this concept of model came. So model is nothing but the representation of the system in terms of equations, isn't it? Then we said okay, modeling we have done, but this modeling has to be appropriate. How many control loops are there? All these things you can find out by finding the degree of freedom in the system. The number of degree of freedom in the system will be the number of control loops you require in the system, isn't it? Then we said okay, we have found out that how many control loops are required, isn't it? But still I have to solve this system. So how we can solve this system? We can use the Laplace transform to solve the system. That is what we said. And therefore Laplace transform came into the picture, isn't it? Now I am saying okay, control loop and everything is done, isn't it? I wanted to find out how my system response is going to behave. Whether the system response is stable, unstable, oscillatory, exponential. What type of response I am expected to get? Can I get the information of this from the equations or not? This is what we are trying to find out. And that is why I am saying that these two slides are extremely important, because if you understand this, you already know the heart of the problem. How to solve the problem, that anybody can do it. But at least understand the problem, that is the more difficult thing, isn't it? In life, formulating the problem is a more difficult task than solving it, isn't it? Okay. So let's look at what I am trying to say. So see, g of s we have defined as a transfer function. Transfer function is what? Transfer function is an equation which relates your output in a deviation form to the input in a deviation form. So it is nothing but y dash s by f dash s, where y dash s is nothing but the output and f dash s is nothing but the input. Both are in the deviation form. Okay. So g of s is nothing but y dash s by f dash s, and typically this g of s is nothing but what? It is nothing but the ratio of the polynomial in s. Remember, that is what we said earlier when we looked at this. I will go back. Remember, when we have solved this, we said that whenever the model equation is there and we apply the Laplace transform, we get the ratio of two polynomials in S. That is what typically we get. So in this case, g of s will also be a ratio of two polynomials in S. Isn't it? P of s divided by, Q of s divided by P of s. Isn't it? So this is what we have obtained, isn't it? Now in this particular case, I have defined the numerator by Zs and denominator by P of s, primarily because if I put Z of s equals to 0, I am going to get the roots of the numerator. And when I am going to put P of s equals to 0, I am going to get the roots of the denominator. Roots of the numerator are referred as 0. They are referred as 0. Zeros of transfer function. So zeros are nothing but the roots of the numerator at which your transfer function becomes 0. Okay. And P of S, if you put P of S equals to 0 and solve and find out the roots, these are nothing but called as poles of the transfer function. So that's why I have represented them by Z and P, so that you can carry forward the same terminology later. Okay. So Z of S represents the polynomial corresponding to 0. P of S represents the polynomial corresponding to poles. This word 0 and pole is very, very important. Later on you will see that they have meaning. We are not defining them arbitrarily. There is a meaning why we are calling them zeros and why we are calling them poles. Okay. So G of S is given as Zs by P of S. Zs is a polynomial in S. P of S is also a polynomial in S. For all practical purposes, you will find this Z of S as a lower order polynomial compared to P of S, isn't it? I can find out how my y is varying with respect to time. I can find out y dash t. I can find out by multiplying this entire term G of S by f dash s and then inverting back into time domain. I can find out y dash t directly from this equation. Again, if we represent this y dash s as G of S into f dash s, let's say this is what the equation we have obtained. Again, for a simplicity, let us assume that this f dash s is a input. This input can also be written in terms of the polynomial in S, isn't it? So that is also represented as Qs by Rs. Okay. That is also represented as Qs by Rs. Now the point to be noted here is f dash s is what? F dash s is nothing but the input. Correct? So this input is coming from external environment. It is coming from external environment. What is G of S? G of S is a transfer function of the process which is coming from the equations corresponding to model equations corresponding to process. Isn't it? Correct? So that means G of S is actually giving me the qualitative information about the process. What will be the actual response, that depends on G of S as well as f dash s both. But here you can see that I can segregate the external environment and the process. Here the process is represented by G of S, whereas f dash s is coming from the external environment. If I have to ask this question, how my process is inherently is, I am asking about the process. Whether the process is inherently stable, unstable, or not, I can find out that directly by looking at G of S. Isn't it? This f dash s is coming from the external environment. Isn't it? My actual behavior, actual response depends on both. But if I say that I wanted to find out qualitatively whether my process is stable or not, irrespective of the input, in that case I only have to look at G of S. Do you all agree? Isn't it? So let's look at qualitatively whether the process is stable, not stable. Remember this f dash s, why we are not including in this qualitative discussion? Primarily because this f dash s is coming from the external environment. It can be anything. Isn't it? But G dash s, it is not coming randomly. It is related with the equations, it is related with the physics of the problem. So it is not random. If you are having a first order process, you will get a specific form of G of S. If you are having a second order process, you will get a specific form of G of S. It is not random. It depends on the process. It depends on what physics the process is involved in. Isn't it? Correct. So I can qualitatively find out without looking at the input whether the process is inherently stable, not stable, whether it is response going to be oscillatory, non oscillatory, directly by looking at G of S. Do you all agree? Everybody is agreeing with me? Okay, now let's look at this G of S a little bit in more detail. So for simplicity, let us assume that this G of S which we have defined as a polynomial, Z of S divided by P of S. Isn't it? For a simplicity, let us assume that the roots of the denominator are given as shown here. So there are two distinct real roots, isn't it? So P1 and P2 are the distinct real roots. Then we are having two complex roots, so P3 and P3 dash, these are the complex roots. And then there is a multiple root, so P4 is a multiple root which is occurring m times. And there is one more root which is P5 which is actually occurring at the origin. I am taking 5 different types of roots primarily to understand how my response is going to behave because of these individual roots. Okay. I wanted to understand how these roots are going to impact my response. Okay. That is why we have selected these 5 different types of roots. Here you can see that we have taken P1 and P2 which are real and distinct. You can consider P1 is located on the left hand side of the imaginary axis, so that means P1 is negative. P2 you can assume as a positive, let's say. P3, these are complex conjugate roots, so that is why they are occurring in pairs, isn't it? P4 is a multiple root which is occurring m times, and the last root which is P5 which is occurring exactly at the origin. Exactly at the origin. Okay. Now this is what the equation we have assumed. Purposefully we have taken the roots like this, primarily because we wanted to understand their impact on the response. How we can invert this in a time domain? We can invert this in a time domain by taking a partial fraction. Isn't it? So in this case, these are the partial fractions. So C1 divided by S minus P1 will be the partial fraction with respect to the root 1. C2 divided by S minus P2 for the second. C3 divided by S minus P3 plus C3 star divided by S minus P3 star. Here, since both these complex conjugate roots are there, that is why we have represented them by star. So you can see that P3 can be taken as alpha plus beta iota, and P3 star you can take as alpha minus beta iota. Okay. For multiple roots, separating the partial fractions is slightly different compared to the usual distinct roots, isn't it? So in this case we will have C41 S minus P4 plus C42 S minus P4 square. Remember, whenever we have a multiple root, we have to take the derivative and find out the constant, isn't it? So similarly, the last root will be C4M divided by S minus P4M, and the last root here is C5 divided by S minus P5. Now let's look at what response we are going to get corresponding to each of these terms. So let's say P1 and P2 are located on the real axis. Remember I said these are real and distinct. Real and distinct. Isn't it? So when I am having the roots which are real and distinct, what type of responses we get? We get exponential response. So that is why we are getting here. So C1 with respect to P1, the response will be C1 e raised to the power P1t. Similarly for P2 we are getting C2 e raised to the power P2t. And again for a convenience, let's assume that P1 is less than 0. P1 is less than 0. So when t tends to infinity, when time tends to infinity, what will happen to this term? This term is going to become 0. Let's look at the second case where P2 is greater than 0. Greater than 0 means this particular root is located on the right hand side of the imaginary axis. Isn't it? It is located on the right hand side of the imaginary axis. So in that case when time t tends to infinity, this particular term is going to become infinite, and therefore your system response is going to be unstable. Your system response is going to be unstable. Isn't it? So you can see that when my root is having a negative real part. Remember in this case P1 is less than 0. So what it means? It is located on the left hand side of the imaginary axis. It is having a negative real part. Isn't it? So where my root is having a negative real part, my system is stable. And whenever my root is located on the right hand side of the imaginary axis, that means it is having a positive real part, my system response is unstable. Isn't it? So I can find out whether my process is actually stable or not stable only by observing the model equation itself. By observing the model equation, I can find out the roots of the denominator, and the roots of the denominator, let's say, all the roots are located on the left hand side of the imaginary axis, it's a clear indication that my system is stable. But if any of the root is located on the right hand side of the imaginary axis, then my system response is unstable. Unstable. Is it clear to everyone? Okay. Now let's look at the second case. Second case is, let's say the roots are imaginary, isn't it? So remember, whenever we are having the imaginary roots, what type of terms we get? We get periodic terms. Go back. This is what we have seen earlier. Isn't it? That's why I am keep on saying all these concepts we are going to use again and again. So see, this is the case when we have seen that the roots are imaginary. Whenever the roots are imaginary, what type of output we are expected to get? We are expected to get periodic response. We will get sine wave, isn't it? That's what we get here. You can see. Ultimately, we get a sine periodic response, isn't it? So same thing we are using here. When my roots are imaginary, in that case the response is given as e raised to the power alpha t into sine beta t plus phi, where phi is a phase lag, isn't it? In this case, this alpha is the real part. Alpha is the real part of the root, isn't it? Now, in this case, there are three sub cases possible, isn't it? When alpha is less than 0, and t tends to infinity, what will happen to this entire term? This entire term is going to become 0. Why? Because this e raised to the power alpha t, this term is going to become 0. So ultimately you will get 0, isn't it? So you can see that when alpha is less than 0, your system response is stable. Why? Because ultimately whatever the oscillations you are having, those oscillations are going to die out and these are going to become 0. You will have oscillatory behavior like this, but these oscillations are going to die with time. This is what is going to happen, isn't it? Correct? And why I am saying oscillatory behavior is there? Because whenever we will have the complex roots, I get the oscillatory behavior. That is what we have seen. Correct? Second case, where alpha is greater than 0, in that case these oscillations are going to increase with more amplitude as we go ahead with time. So my system response is unstable, isn't it? And when alpha equals to 0, then I get a sustained sine wave. Which is not increasing, the amplitude remains the same. You get a sine wave, same sine wave throughout. So it's not becoming unbounded. So when the system response is not becoming unbounded, what it means? It is stable. Okay? So whenever alpha is 0, I get a sustained sine wave and I get a oscillatory behavior. But when alpha equals to 0, what it means? When alpha is 0, what it means? It means that the roots are located on the imaginary axis, which has alpha value, which is the real part is 0. So roots are located only on the imaginary axis. That is what it means. Okay. So in that case, you get a sustained sine wave. And the system response, we call it as a critically stable, marginally stable. Isn't it? That is what it is called. Multiple roots. Anyway, we will come back to this. I think this time over. We will again discuss the same thing one more time in the next class. This is a very, very important concept. If you understand this, you will understand this course easily. Otherwise, we have missed the class. Okay. जाना है ना लैब जाना है हाँ
जाएगा ना
चलना है अभी मालूम है
अच्छा ऐसा ऐसे तो ये बना लेंगे ना पूरी फूड के सामग्री